A very interesting and niche technique is to do the integral of the inverse function. Now, here is the identity we'll be using. The integral from a to b of f of x plus the integral from f of a to f of b of the inverse is equal to bf of b minus af of a. Now, this seems counterintuitive, however, it does hold true, and it will be very useful if we find an integral where it'd be easier to calculate the inverse of a function rather than calculate the integral directly. The best example to use for this is the integral of the Lambert-W function. Now, the Lambert-W function is dubiously defined, however it is the integral of f of x, the inverse of f of x, where f of x is e to the x e to the x. So we have our original function, and we are looking for the limits. So f of a is equal to 0, and f of b is equal to e. Well, in the first case, x must be 0, and in the second case, x must be 1. So now we have our limits. We can substitute everything into the original identity. We have from 0 to 1 the integral of x e to the x, plus from 0 to e the integral of the Lambert-W function, is equal to bf of b, well this is 1 times e, minus af of a, which is 0 times 0. So now, if we want to solve our original integral, which is the Lambert-W function, we can move the other integral to the other side. So we have e minus the integral of x e to the x. Now this is solvable with parts, so u equals 1, v dash is e to the x, u dash is 1, v is e to the x. So when we do uv minus the integral of u dash v, this is what we get, e minus x e to the x from 0 to 1, the integral from 0 to 1 of e to the x. So the first part, we have e minus 0, and the integral of e to the x is e to the x. So we have e minus 1. Now, these cancel each other, these two minuses cancel each other, so our final answer is e minus 1. Now let's use another example, which is really interesting, a lot more interesting. We have 0 to 6, the integral of the cube root of x plus the cube root of x, and so on until infinity. Now, when I first look at this, I might think we can use some kind of series. However, it would be easiest to use this integral of inverse technique. If we let y equal this function, you will realize that we have y equals the cube root of x plus y. Now we can cube this. Y cubed equals x plus y, and then y cubed minus y equals x. Now this is our inverse, and what we need to do now is find the limits. So f of a, which is 0, f of 0, what does f of 0 equal? Well, if we put 0 into x, there's an issue because there are multiple ways when we factorize that we can get 0. So what will be our lower limit? Well, to figure this out, we can look at the graph. Now this identity only holds when our function is injective from a to b, which just means 1 to 1. However, if we graph this function, which is a cubic, around the origin, we get something like this. And say 2 is somewhere around here. We have -1, 0, and 1. From -1 to 2, are we injective? Well, no, because of this part here. And from 0 to 2, are we injective? No, because of this part here. However, from 1 to 2, so around this area, the function is only moving in one direction. So this will be our lower limit. And our upper limit, well, there's no explicit way of solving this. However, if we put 6 into x, you will notice by inspection that 2 works. So, substituting all of this into our equation, we have the cube root of x plus the cube root of x, and so on, the integral of that, plus from 1 to 2, the integral of x cubed minus x dx, the variable doesn't matter, I've substituted x for y here, is equal to bf of b, which is 6 times 2, minus af of a, which is 0 times 1. So, once again, let's move the integral that we can solve to the other side. We have 12 minus the integral from 1 to 2 of x cubed minus x. Now this is just a very nice, simple power rule. So we have x cubed over 4 minus x squared over 2. From 1 to 2, let's substitute this in. 2 to a 4 over 4 is 4. 2 to a 2 over 2 is 2. And then we have a quarter minus a half. So we have 12 minus 2 minus a quarter, which is 10 plus minus a quarter, which is 39 over 4. And that's our answer.